Alright, so I'm going to go through these problems and explain calorimetry to you guys. And I think the main thing, the most important thing for you to remember is that when we're talking about calorimetry, what's happening is you're putting a piece of metal, hot metal, into a calorimeter. Now this is the calorimeter. We use styrofoam cups for our calorimeters, which obviously allow some heat to be lost. But we took the hot metals, I'm going to draw it in red, and we put it into water in the calorimeter. And so what's happening is that the metal is going to be losing heat while the water is absorbing heat. And so the way that we would represent this, we would say the Q of the water, so the heat that the water gains, equals the heat that the metal lost. Now we show a negative Q because that negative represents losing of heat. Now, an important thing for you to note is that this is not perfect. This actually didn't happen in the lab. All of the heat that the water absorbs, or all of the heat that the metal released, was not absorbed by the water. You lose some heat in certain ways. So for example, when you transferred the piece of metal into the cup from the beaker, it lost heat there. This styrofoam cup system is not a perfect insulator, therefore you're going to lose heat again. But we're going to make this assumption even though technically it's not 100% correct. So the first thing that I'm going to do for calorimetry problems is I'm going to determine the heat of water, the heat that the water gains. All right. Now the reason why I'm going to do that is because I know the specific heat of water. I do not know the specific heat of the metal I'm working with. So instead, I'm going to solve for the heat that the water gained, the Q of the water, and then I'll be able to solve for anything with respect to the alloy once I have solved for that. So I'm going to start off with water. Okay. Now, for the water, your formula for heat is Q, heat, equals M delta T times SH, which is your specific heat. Now, I'm solving for Q, so I'm going to leave that as it is. The mass, if I read through this problem, the 25 grams here is for the alloy. All right, so that's not the mass of my water. The mass of my water is 90.0 grams. Okay, I need to multiply that by my change in temperature. So let's figure out change in temperature over here. Remember, change in temperature is T final, your final temperature, minus T initial. Okay, so remember here it tells me that the water rose to this, so this is my final temperature. This is the temperature that it started at. So I've got 27.18 minus 25.32. And what you will end up getting for your delta T is 1.86. Now I've stayed true to my number of decimal places, so we're all good there. So I'm going to plug in my 1.86 here, that's degrees Celsius. And then I'm going to multiply that by the specific heat of water. Now I didn't put this in the problem and I would give this to you on a test, but your specific heat of water is 4.18. Okay? So when you multiply these out, what you get is 699.7 joules. Now I want, this has 3 sig figs, this has 3, this has 3, so I want 3 sig figs. The way to round this, you have to make it 700 point joules. That makes it 3 significant figures. All right. Now, what I'm going to do, one sec, I'm going to make my font this smaller. This is the heat that the water absorbs. Okay. Now, that will be the heat that the metal released, except it's just going to be the negative of that. So now I'm going to deal with everything with regards to the metal. I've got the same formula, Q equals M delta T times your specific heat. And if you read the problem, for this, what you're trying to solve for is your specific heat. Okay? So what I need to do, I know the Q is going to be negative 700, because I got that from the water problem. Your mass, the mass of the alloy of the metal, is 25.0 grams. Okay. Now your change in temperature, let's figure this out on the side. Remember, the final temperature of my water is the final temperature of the metal. And the reason why is once the temperature has stopped changing, that means that there's no longer a transfer of heat. And if there's no longer a transfer of heat, that means that there's no difference in temperature between the metal and the water. Because the only time heat is transferred is when there is a difference in temperature. So for here, this is going to be my final, so delta T. My final temperature is 27.18. My initial temperature of the metal was 100 degrees Celsius, 100.0, all right? And so what I get for a change in temperature for here is negative 72.82. Okay, and that's degrees Celsius, so I'm going to plug that in here. Okay, so that's mass times my change in temperature, and I'm solving for my specific heat. So what you've got to do, if you can do this without my help, you can fast forward me. I've got 700 point equals, I need to multiply the 25 times the negative 72.82, and I get negative 1,820.5 times your specific heat. And so I'm going to divide both sides by the negative 1,820.5 to get the specific heat all by itself. Okay, so this will cancel. And so when you do this negative 700 divided by that, you get so your specific heat equals 0.3845 joules per gram degree Celsius. Okay, because it's heat divided by mass and change in temperature. Now, from here I want 3 sig figs 3, so I want a total of 3, so 0.385 joules over gram degree Celsius, and that's it. Okay, so notice in these problems, what I always do is I start off solving for the heat that the water will absorb, and then I can solve for anything with respect to the metal. So let's try the next one. I'm going to go a little bit more quickly with this one. I start off with water, trying to solve for the Q of the water, so the heat of the water. So Q equals M delta T SH. Okay. The mass of my water in this problem, just read carefully, it's not 10, it should be 200 grams. Okay. Change in temperature, my final temperature is 25. My initial temperature is 20 for water, and so my change in temperature is 5.0. My specific heat of water stays the same at 4.18. And what I get is 4,180 joules. Now remember, I want only 2 sig figs based on this, and therefore it's going to be 4,200 joules. Now, that is the amount of water that is the amount of heat that the water absorbed. So that will be equal to the amount of heat that the metal released, so it's just the negative of that value. And I'm going to be using the formula, sorry, I skipped a step. I'm going to be using the formula Q equals M delta T times SH. Okay, so that's my Q there, that's the amount of heat that the metal releases. The mass is 10.0 grams. If you read the question, actually I'm going to undo that. If you read the question, it's asking for delta T, the change in temperature, so I'm going to leave that alone. And then the specific heat is given to you, it's 0.40. Okay, so what you'll get is negative 4,200 equals 4.0 times your delta T, because I multiplied the 10 by the 0.4. Okay, and then I'm going to divide both sides by 4.0. Okay, and then that means my delta T is going to be equal to 1,050. My units are degrees Celsius, and notice it's negative. Okay. Remember, this has you've got 2 sig figs, 3 sig figs, 2 sig figs, so I need 2 sig figs, so it's negative 1,100. Please don't just write negative 11, I will cry. It's bizarre how people round that way. it should be in the thousands. All right, so that looks great. If you're thinking to yourself, does that make sense that the change in temperature should be negative? Keep in mind that the temperature of the metal is going to be decreasing while the temperature of the water is going to be increasing. So yeah, it should be negative. Now, for the next question, basically what it's asking you to determine is, what is the initial temperature of the metal? If you left the hook in the Bunsen burner, it's assumed that the hook will reach the same temperature as the Bunsen burner. Just like when you're boiling water, you assume that the metal in the boiling water had the same temperature. So we're going to use the delta T formula, TF minus TI. I know the change in temperature, it's negative 1,100 degrees Celsius. My final temperature was given to me here, 25.0 degrees Celsius, minus TI. So the first thing I'm going to do is subtract 25 from both sides. And so what I get is negative 1,125 degrees Celsius equals negative TI. Now since there are two negatives here, those will cancel. And so you get that your initial temperature equals 1,125 degrees Celsius. Remember, since you're adding it, it's based on decimal places, and since this has one decimal place, this has none, my final answer should have none, so there's your answer. Now, let's make sure that makes sense. Does it make sense to say that if it started at this, and the change in temperature was a negative number, that it would go all the way down to 25? And the answer for that is yes, it does. All right, so that's all there is.